Welcome to our first session, and today we are kicking off with the sciences, and rightly so, I think, to a great extent. Liberal arts education is often dubbed to be only the arts and not the sciences, and I couldn't have been more excited to actually start with the sciences panel today. And let me quickly introduce the panelists and to our panel topic today, which is infinite possibilities with the careers in sciences. We're joined by Somdatta Karat. Somdatta has worked for more than 6 years as a full-time school teacher, and she's a science communicator at the CSIR CCMB. She's completed a PhD and postdoctoral work at the George August University from Germany, and she's also been a Teach for India fellow in Mumbai. We're joined by a few of our own, Dr. Lakshman Varanasi. Dr. Lakshman is an assistant professor of biological science at CREA. He holds a master's in life sciences from JNU and a PhD in biochemistry from the University of Mississippi, the USA. Dr. K.S. Vishwanathan, whose research interests has spanned in the areas of molecular conformations and weak covalent interaction, which pervades through all of chemistry, physics, and biology. And he has a PhD from Vanderbilt University. We're also joined by Professor Shiva, our division chair for the sciences. Professor Shiva is a theoretical physicist, and he's interested in quantum and classical dynamics and statistical physics. He studied at the IIT Madras in Chennai and joined the Department of Atomic Energy as a scientist. I mean, this couldn't have been more exciting. We actually have one academic from each sciences and an organization like the Center for Molecular Biology. So thank you so much, panelists, for joining us today. And I do look forward to a very conversational, free-flowing session. I'm going to start this first question, the first round, really about getting your perspectives on how do you see the study of sciences has moved. You know, in the we could kind of take a decade almost as a year piece, if you like. So Somdatta, I just wanted to ask you, so in terms of your work and what you're seeing at the CCMB, for instance, how have you seen the study or the careers in the sciences move from a basic science degree? Are you seeing some changes from what's traditional to what's now?
Yeah. So in biology, for example, when I was a student, there were three major paths that people would take pursue as a career. They would either become academics, and generally, when I speak of academics, they would generally be guiding PhD students, or maybe work with universities and guide undergraduate and postgraduate students. Then there would be people who would work as scientists in national laboratories or work with industries, but as scientists. But over the last 1.5 decades more or so, all of these three different spaces have changed significantly. Now, people who want to teach are not only considering undergrad and PhD students to mentor and guide, people are also thinking of working with schools. I, for example, did that. Then people who want to work as scientists, earlier, there was a lot of distinction between basic science and translational science, and there would be institutes which focus on only one of them. Today, there's a huge, immense emphasis on bringing the two together. So either institutes are needing to work both of these kinds of questions in their own institute, and if they're not able to do that, then there's a huge emphasis for them to collaborate with others who are doing that. Then industry, people, of course, are still working in industries as scientists, but at the same time, many more startups have come up. So you're not just working for an industry, there's a possibility for you to start your own enterprise, work on your own question, think of what product you want to bring about. At the same time, because now there's so much emphasis on everybody to collaborate with each other, the number of stakeholders that each one is dealing with has increased manifold. That has also led to a lot of managerial roles. So that includes looking at IP, looking at business development, looking at communications. Then there's research development where there are science advisors who keep a track of what kinds of cool questions or important questions are there in the field that one should look at and one has the capacity to look at or need to look at. So those exist at all kinds of levels now, from the government to institutional levels, or what used to be called, there's also consultants for those. So I think in the last 1 decade, I would say that crosstalk between different disciplines and different subjects has just immensely increased, and that has also led to an evolution of a lot many more career paths than what I used to see when I was a student.
Yeah, thank you. And I'm sure we'll explore a little bit more as we keep talking about this. I'm going to ask Professor Lakshman this, and thanks for joining us. So you've kind of started with that area of biological sciences and you went ahead to do your PhD in biochemistry. Do you want to just talk through the bit about how that movement happened? And can you also just highlight through what are some of those major transformations that's happening in the biological sciences area as well?
Sure. Just to do a sound check, Kala, can you all hear me properly? Okay. So, I started off doing a degree in the basic sciences, biochemistry, microbiology. These were my subjects in the undergraduate, at the undergraduate level. I went on to the master's and I wasn't sure, what I should study, because when biochemistry, all the sciences, all the biological sciences appeared equally interesting.
Mm.
And I decided, okay, maybe I should find out more about these areas before I identify one area and decide to stick to it. So I went on to JNU. They had a very umbrella kind of master's course called life sciences.
Mm.
And that really, helped me understand where I would be going if I chose a certain area. If I decided to specialize in something, what would I expect? And that's when I chose biochemistry. Of course, the number of things that a specialization in biochemistry allows you to do in the biological sciences appeared to me to be more than, for instance, with a PhD in, say, genetics. But it's not so. At that time, that was the perception. So, when I specialized in biochemistry, I observed this transition in the United States. So I can, I returned to India just a few years ago, so I can at least talk about that, and maybe some will identify with that. There was quite a bit of emphasis. The NIH in the United States was funding basic research very well for a long time. And then they decided that fundamental research would be funded only if you could show a relevance of your research to human health. So that made all these basic scientists focus on how they could pitch their research as something that's relevant to human health. It's not a good thing in my opinion, but that was one of the transitions which happened over the years, right? And you found yourself, you found the population of students who were graduating from basic science degrees, basic science PhDs, gradually migrating into the health sciences, right? And so but this is the point I want to emphasize, that you need a deep grounding in the basic science before you can find ways in which you can apply it. Right? An application presupposes the knowledge and the science, right? The technology comes over later, but so for instance, and I could give you more examples, and we'll talk more about this later. But I think what has remained, what has remained the same is the focus and the importance of the basic sciences has not waned. That is still just as important. You will find after you specialize in the basic science that you can actually go on to apply your knowledge, which is what I did, right? But the knowledge has to be there. So I think regardless of the changes, I think this is one thing that has remained constant. And I would like to highlight, emphasize that a degree in the basic sciences is still just as important now as it ever was.
Fair enough. The foundation, you think, should just definitely be very strong with the basic sciences before you go ahead and apply. And definitely we'll come back to the whole applied end of it, as well, for sure. Professor Shiva, I'm just going to jump to very quickly on the physics end. So just your thoughts around, physics more specifically across, and I know it's kind of seen all sorts of interfaces, physics with technology and physics with, we are talking about your area as well, the astro end on the quantum end. What are you seeing as some of the major changes that has happened just in the study of physics in the last few years?
Shiva, your mic is...
Am I audible?
Yes, thank you.
Thank you. So the time when I did my master's and the PhD program, the introduction of physics used to be historical. So whatever struggles they had, that's what they would introduce. But then there was no practically time left to learn what's currently happening. So in late 80s, people started rethinking this. So now what they do is they start telling you what's currently happening. And then they relate it to how these ideas came into being in a historical sense. And I feel that is a more efficient way to learn the subject. Otherwise, you will, by the time you graduate out in 2020, you would be knowing physics that happened in 1930s. So in order to avoid that, this is required. And second thing, in something around 50s to almost, I would say even around late 70s, people thought doing fundamental physics is not very good. It should always be applied physics, in the sense almost bordering on engineering. And people should know not that every day one jumps out of the bed, today I have a gadget to give it to the public. It doesn't happen. And in 85, when Richard Feynman talked about minuscule objects, minute objects, which can be manipulated to do wonderful things, this area called quantum information came into existence. Now, every big company that you can think of, they are pumping in billions and billions of dollars into this. And every subject has a quantum as an adjective: quantum biology, quantum politics, quantum finance, of course, quantum physics. So this seems to be playing a very, very vital role in, not that the quantum mechanics is directly applied, but the ideas and the mathematical concept that we use for quantum mechanics seem to have a very wide universal applicability. So this is the right time to jump into emerging frontier area, I would say, because job opportunities, and it will challenge you because these ideas are simple, and because they are simple, it is equally challenging to apply them in complex situations. So this is where I feel the subject is heading. And one nice thing about physics is that, as you rightly pointed out, Kala, that it ranges from something that we can't see because it is too small to something that we cannot see because it is too big, the entire cosmos. Okay, so it ranges, it tries to accommodate all these things with a handful of principles. Okay, and that nothing is more economical than that, in my opinion.
Yeah, it could be a problem or an opportunity, both ways, whichever way you want to look at it. But that's very interestingly put. And we'll come back to a bit about asking you your area and a little bit more on quantum on that. So, Professor Vishwanathan, I wanted to move to you on the chemistry end. And as I said, this is about breaking myths. And I have always grown, I'm an economics graduate, I've always grown looking at my chemistry colleagues saying, oh my God, your life is going to get confined to a lab. Now, is that a myth? I really want to know that. How does chemistry go beyond just the lab, and how does it really, how has it moved to apply to something that's beyond it?
It's a myth. When you do chemistry, it is not that you get confined to a lab. So that's the straight answer to what you said. Now, let me build on that. The way chemistry is applied today, it's applied to biological systems, it's applied to environmental sciences, it's applied to astronomical phenomena. You have a very growing field of astrochemistry and so on. So it is not that you're confined to a lab. You have to go out in the field and start applying the knowledge of chemistry that you have to things that are around you. And eventually that's what makes it all the more interesting. Of course, you do the very important and fundamental experiments in the lab, but then you take it over to the field in applications such as what I've just have mentioned. And of course, in addition to that, you have computational chemistry today that's grown to such an extent, where you cannot do experiments and be done with it. You have to bring in the computational aspect to explain what your experiments are really saying. And I've always said, and in my own research, I've applied it. I always call myself as an experimentalist who pretends to do theory, because our group does both, but I'm basically an experimentalist. But you have to have your computational studies to justify what or to at least corroborate what your experiments have shown you. In fact, I believe that experiments without theory, is lame, and theory without experiments is blind, because you can't just have your theory with no experiments to support it. So yes, chemistry goes much beyond the laboratory, and that's what actually makes it that much more interesting and useful to the society.
Thank you. So that's really just setting the ground in terms of having all our panelists agree that clearly the sciences in the decade has moved beyond, while it does still have its heart in the core and the fundamentals of what we're saying. It's really traversed to a few other areas. And I want to really talk about how sciences now interacts with other disciplines. And that's really what we'll talk about. And I'm going to come back to you, Professor Lakshman, on this, that and we know you're actively engaged with industry through your scientific expertise. You work with healthcare technologies and biomed technologies and all of that systems. So how do you see biology interact with other disciplines in that settings? And where do you see, for instance, healthcare being now? I'm kind of seeing this unprecedented interest from our students as well, wanting to make a career in healthcare. And hence, how do you see, what kind of disciplines do you see biology interact with in that healthcare realm more broadly?
It's a very relevant question, Kalab. So thank you for that question. So if I may just step back and talk about a certain experience. There used to be this dichotomy when you were in +2, whether you had to choose medicine or you had to choose something else, right? So there were those who would not choose either and do basic sciences, right? So here's the thing. So I sort of moved back to India from my research position in Europe at the end of 2018. I had been working on cancer biology, first as in the basic science capacity, and then as a translational scientist in Europe. And we worked on cancer, about how we can apply that knowledge, to detecting cancer earlier, right? And so when I moved back to India, there was this desire to interact with industry, to try to apply my knowledge, my learnings to, say, an application, right? And eventually, in the beginning of 2019, I happened on a company named HealthCon. It's based out of Hyderabad. It specializes in personal health records, and they have this what they call an ICU in a box. Essentially, allows you, a doctor, to monitor a patient remotely. It has the ICU in a box measures all the vitals that you would have in an ICU, right? That you could measure in an ICU. And the reason I was taken on was because they needed some biomedical backing to the work they were doing. They were going in blind. I mean, they were doing it as a device, but they wanted to know how they could make it better. Like, what is the biology that is required there? And so, for instance, it's important to know that there are certain variables that you can collect from a person, certain vitals you can collect. And there is a way, this actually is a nod to the mathematics really. There is the mathematics and the computer science has evolved enough for us to be able to predict, based on what we know about a person, we can predict whether or not the person will have experienced a disease, right? And so that's one example of how my knowledge of cancer and what predisposes a person to cancer could help, or any chronic disease could help a company make its product better. I think especially in the area of electronic health record, which is a computer science application, right? So that's one aspect of it. There are other areas in which other ways in which, for instance, a degree in the biological sciences, or a knowledge of basic biological sciences can help, right? For instance, we have the drug industry, right? So we are not doctors, but I should say that we are the doctors' best friends, really. For instance, when I was working in the translation, at the Institute of Translational Science in the Czech Republic, our job was to interact with physicians in the hospital. They would provide us the samples, the cancer patient samples. We would analyze these, we would investigate these samples and tell the doctors what it was in the cancer patient's blood that was different from a healthy patient's blood, right? They didn't have the expertise to do this. But, we had a conversation happening, we had a dialogue going. And this was one very nice way where we could apply our basic science knowledge in curing disease. We call it the bench to bedside, a bedside to bench to bedside circuit. It's a way of making that smaller, right? There are other ways, right? All chronic diseases, for instance, a knowledge of, for instance, gene editing, we call it, you might have heard about, everyone here might have heard about it, it's called CRISPR-Cas, right? Now,
yeah.
this technology for editing a gene, a defective gene, and replacing it with something you want, arose because someone was studying about a bacterium's interaction with the virus. Right? So it arose from a pure exploration, blue sky research, right? So that's another way, right? I mean, there are many such. The drug industry, for instance, there was a Nobel Prize awarded for immunotherapy like a year or two ago, and it all arose because they were studying about how, what is it? Why does the immune system not fight the cancer, right? I mean, what is the science behind this? And once they were able to understand the biology, they were quickly able to apply it to develop drugs that would stimulate the immune system to fight the cancer, right? This is just another example. If you look at the agro-tech industry, right? For instance, how do you increase food production? Right? I mean, how do you, or for instance, pest control, right? How do you take care of, say, garbage, for instance? So the more we explore, for instance, how bacteria quickly degrade different types of materials, the better we'll be able to apply it. And I see this happening across the board. Like, I mean, there's a proliferation of areas in which you can apply basic science, and this has been facilitated by the administration's push towards startups and funding startups, and this has really allowed given scientists some leeway in which to apply their knowledge and their skills. But I won't go too far. I mean, please keep me on track because those are the different.
Yeah, that's quite a fair, in terms of I guess the interfaces seem so much more broader. You could either talk about pesticide from the agro end, or you could talk it from the nutrition end, and it's across the board. And you really did touch on CRISPR. I mean, it's something that's very close to my heart, and I kind of track quite very closely in terms of what's happening in that space, and the amount of investment that's actually going into the area of genetics itself is quite fascinating. And that I don't, correct me if I'm wrong, but somewhere that all that work around the CRISPR and what's happening in the genetics, going back to how societies, to people, to their food habits, the nature. It's going back to that social studies to some extent, which then again links back to policy, and hence you kind of say how some healthcare policies for some countries work very differently. So it's quite fascinating that you did put it that way, and we'll come back to that. And I will kind of move to Professor Vishwanathan here very quickly. In terms of, Professor, your research area, really for me, it's like, the Trimurti of physics, chemistry, and biology coming together. And I've kind of find some of that very unique. So do you think that more so now, I don't know the history, but more so now, that these three sciences are coming together, and where do you see them very forcefully coming together to solve some of the complex problems?
Yeah, my work, as I said, I use the tools of physics, which is spectroscopy and instrumentation. I use methods of the molecules of chemistry, and then the results are basically something that could be used in biology. So that is where the confluence is. But I don't think it's unique. What I've done is it's not unique at all, because if you look down the ages, since the time the Nobel Prizes were instituted, if you go back and just look at the Nobel Prizes and the way the Nobel Prizes have been given, you will find that the distinction really didn't exist between physics, chemistry, and biology. There has been no distinction. And I always keep saying this, when plants do photosynthesis, they don't label themselves as a biologist or a chemist or a physicist and then do photosynthesis. They just do it. Now, it's our inability to understand the whole of it. So we break the problem down into various pieces and then say, okay, I'm a chemist, I will use the tools of chemistry to study it. The physicist will say, I will use the tools of physics and study that. And likewise, the biologist will do that. And then we put all the three pieces together. It's the proverbial blind man and the elephant, trying to feel the elephant and giving you the entire picture. So there has to be this give and take between these various subjects. And this labeling of subjects as being chemistry or physics and biology, I think is probably not a great thing, but we still do it because of our inability to fathom the entire thing together. I'll give you some examples. For example, Curie got a Nobel Prize in physics in 1903 and the chemistry in 1911. But she was still doing the same type of research.
Mhm.
She was working on radioactivity and so on. But at one time, she was given the prize for chemistry, and another time for something very similar, she got the prize for physics. Peter Debye, for example, who I'm very sure Shivakumar would swear that he is a physicist, actually got a Nobel Prize in chemistry in 1936 for his work on dipole moments and so on. And the other very glaring example of this borderless studies, if you take Venkatraman Ramakrishnan, who got the Nobel Prize in 2009, he was a physicist by training who used, problems in biology. He solved problems in biology and got a Nobel Prize in chemistry. So therefore, you can see that these borders are basically not very, very, very strong. They're very virtual borders, and therefore, very often when you study something, there is always some physics that's going to be linked up to it, or there'll be some biology that's going to be, latched onto it. And therefore, it is always good to see. As a chemist, I don't think one should, if I do chemistry or physics, I don't think you should label yourself as chemist and say, I'm going to exclude anything that is physics. No, I think you have to keep your eyes and ears wide open to see what the other subjects can give you in the solution to your own problem. Even when Lakshman said, for example, he said that he consulted, he would talk to doctors and for coming up with some methods to analyze some blood, maybe to find out what the situation is. I'm very sure the techniques to analyze the blood probably came from physics and chemistry concepts, which biologists use to solve healthcare problems. So these are borderless studies, and one should be aware of that. You could still do your chemistry, physics, and biology as a degree and then come out of it because of the fact, as I said, we can't study all of them and, be masters at all of it. Therefore, these are virtual borders. You must recognize that and always be ready to accept and, ideas that come from other areas. And this is something very, very important which scientists should keep in mind. Don't label yourself and get stuck with it.
Yeah, no, absolutely apt. And yeah, segue very nice to the next round, but I'll come back to that. Somdata, I want to really ask you a bit about, what you're doing, and congratulations to CCMB on a fantastic, work that you're doing at CCMB and at the forefront of COVID itself. So the center itself, the Center for Molecular Biology itself, calls itself that it's in the center of modern biology and interdisciplinary biology. Now, can you just shed some light on what modern biology actually means? And in terms of interdisciplinary biology, where do you see that interface with other areas probably in the work that you all do at CCMB, or more broadly from your perspective?
Sure. So modern biology basically looks at biology from the cellular and molecular details. And because one looks at cells and molecules and has to play with them, it automatically also necessitates to be interdisciplinary, because one needs to create these tools, like just Professor Vishwanathan also said, that to be able to look at blood samples, for example, we have needed to create tools that are based on physics and chemistry. So that's pretty much what modern biology is. And I think that definition has the most amount of significance in explaining how to look at biology today than, let's say, what used to be the case 50 years back, when natural history was the major way. Not 50, but a little more than 50 years back, when natural history was the only way many people would look at biology. So that paradigm has changed in biology. And today, any reputed biology research institute or university would have physicists, chemists, engineers, clinicians working together. Some places would also have public health experts, epidemiologists, coming together. Bioinformatics, for example, is hugely needed. Computation and informatic tools are hugely needed in solving many of the key biology questions or life science questions people are dealing with, because they all require big data analysis to be done. So that's how the disciplinarity of biology looks like currently. And let's say, I mean, you brought about the topic of COVID and CCMB being able to work at it at quite a forefront. And I personally think that that has been able, because of the mix of different disciplines of people that are at CCMB. We have molecular biologists and cell biologists, of course, and that has probably led us to be able to create new ways of testing. We have bioinformatics department, which has, and bioinformatics as well as infectious biology scientists working with us. So that has enabled us to grow the virus in our institute and do genome sequencing and genome surveillance over it. So in addition, we also house a lot of startups or have a huge connect with industry space in Hyderabad and across India in general. So that has also enabled us to crosstalk with industries, which has been very important during this crisis. So that, I mean, COVID probably is an apt example to talk of how crosstalks are happening or also need to happen in biology today.
It's quite interesting that you did connect it to a bit about what's happening in the business, what's happening in the computing space across the board. So thank you. Yeah, we'll come back into that space a little bit. Professor Shiva, just asking you a bit about physics as such, and I know we touched in the last conversation in the last round, in terms of asking, where do you see physics increasingly more interface with, in terms of, one is within the other sciences, but going beyond the other sciences, the other realm of humanities or the arts, do you see a little bit more interaction of physics at all into any of those realms?
Yeah, sure. Before I answer that question, maybe I just want to add something to what Professor Vishwanathan said. Sure. This demarcation into physics, chemistry, biology, these exist in our textbooks in the school particularly. Okay. But Erwin Schrödinger in 1950 wrote a book, What is Life? He is a Nobel laureate in physics, but he wrote a book titled What is Life, which actually set the tone for what we call as modern biology, where you ask fundamental questions at a molecular level. He was the first person, but he got Nobel Prize in physics. Okay. So these distinctions don't really exist in the minds of really professional scientists. And coming to a question like the relevance of physics in other contexts beyond the sciences, as I told you in my answer to the earlier question, I do see books titled Quantum Politics, okay, and Quantum Finance. And in fact, some very well-known physicist who is also in the National University of Singapore even questions the way economists try to decide the status of a nation in terms of its economy. They say they've not understood. So, of course, this could be a rhetoric, I understand, but definitely ideas from physics are being used beyond sciences. That much I can tell you. And if you even ask at a very mundane level whether physics is helping, we know now like some old, let us say, a sculpture or a painting, and you want to know how old it is or what kind of paints are there. The conventional method is actually to scrap a part of it and then take it to the lab and analyze and get all the components. But it's also possible to just looking at it using the right instrument. Okay. Who would have imagined that somebody could measure the temperature without a thermometer? Now, if you go every day, the doctor will just to show a IR thermometer and tell you the temperature. Okay. And the oximeter that we use, previously they have to take out a drop of blood and figure out. Now you just put that clip over your finger, just by shining a bright light and looking at the reflected light and changing the spectrum, it tells you what is the level of oxygen. So it is which we call as a non-destructive testing. So physics is also useful to art historians and on art restoration that way. It's very helpful. And now when you want to talk about, let us say, there is an industry somewhere, effluents are let into the ground or water, and you want to see how far it can go and affect. So it has some implication for public health. And who will be able to tell you how far it will diffuse and go? Naturally, you end up with a physicist who will be able to tell you exactly how far it can go, where all it can contaminate water bodies or land. So it does have implication for almost everything. See, originally all these subjects were called natural philosophy. Okay, and these names, physics, chemistry, biology, are all post 1800. And therefore, the original name, in my opinion, still holds. It's natural philosophy, and it applies to every aspect of our life. So that would be my answer.
It's quite interesting because I did have, we had a set of questions that came for this panel before. And one of the questions was, if a student somebody wants to study science and politics and interested in science and humanities, can they do it? So that question itself to some extent assumes that both are separated and cannot be done together. So interesting.
Maybe I can. On a hilarious note, I can tell you our former finance minister, Madhu Dantavate, he was teaching physics.
Wow, there you go. So the fundamentals and the I guess the approach to the science is what makes it different than just the discipline itself. And I'm going to come to, so just to seal this whole discipline specific discussion, and then we move to the future, I want to come through a round of a simple yes or no. And I'm going to ask you, Professor Shiva, now that you unmuted and you're here. So to succeed for today's student, to succeed in the world of what we call progressive science, it's important then that they should shed the blinkers of a particular single discipline and approach all other disciplines with equal interest. Yes or no?
I would say yes. When I say equal interest, use your subject to view other disciplines. That is where new perspectives will emerge. It is not that I learn physics and I learn philosophy or politics and keep them as individuals. No, I learn politics, but then I look through the prism of physics, or vice versa.
Somdata, your response? Thank you.
An absolute yes.
And Professor Lakshman?
I would say yes. I mean, you still need to specialize. I mean, you need to get some deep knowledge, but it's important to be very open and to constantly be abreast of, how we can use other disciplines to supplement your work.
Yeah, we often talk about the T being the while you don't really lose that depth, don't really just go your line in that singular focus. And Professor Vishwanathan, I'm assuming it is.
It's a yes, and exactly the way Lakshman put it. You have to keep your eyes open to inputs from other areas, but you also have to specialize, because at the end of the day, you can't be a jack of all trades and then hope to get big on it. So you have to specialize, and you have to pick up some tools and be good at it, but at the same time being aware that there are other tools that you could use.
Yeah. Thank you. I'll keep you on hold there, Professor Vishwanathan, and start with you. And this is really the last segment in terms of a lot of young students in here, parents, counselors, all signed in. And I really wanted to go through the bits about your top thoughts and advice to any graduate who's looking, whether they want to look at it as physics, chemistry, biology, or the sciences itself. So if you were to talk about, hey, look at these big movements that's happening, keep your eyes and ears open to some of these things. So what could be the type of, let's say, study areas or the research questions or the big problems that you think that they could think about or bear in mind, that you think today, it could be just confined to your space, that a graduate of tomorrow we need more application in this area. So your thoughts?
Well, the two most important areas that all of sciences should be looking at and will be looking at is going to be environmental and healthcare.
Okay.
There's no question that, all that we study, eventually there must be important questions asked in the areas of environment, areas of healthcare, and so on, because these are the two major issues that's going to be plaguing us. And we're already seeing it happening, and it's going to get even more serious. And therefore, all of these studies that we do must address these questions, and one must equip ourselves to be able to ask the right questions. And that's the harder part. Answering a question is not that typical. It's asking the right questions that's going to be harder. So I think that's going to be the areas that the big things are going to come in these areas of healthcare and environment. And whether you're a physicist, chemist, biologist, or the political scientist, economist, or what have you, I think these are the questions that you will eventually have to address and answer.
And did you also think an area like environment that you touched is so interesting, because most often, again, the large environment think tanks tends to have different science disciplines pulled together, isn't it? More so now than before.
No, it's always been the case. I think, as I said, these demarcations that we have put, but But the fact is that environmental science has always been, and healthcare has always been supported by work in chemistry, physics, biology, and what have you. Um, the physicists, for example, have had huge roles to play in how the diffusion of various pollutants occur through the air and so on. The chemists have had a huge role in figuring out the basic mechanism, why some compounds cause the ozone depletion, why how the greenhouse effect really works, the exact mechanism, and so on. And physicists and chemists have had a huge role to play. The biologists come in because there are, anthropogenic factors and, plants contributing to all of this. So I think all of the sciences have to put their heads together to be able to answer these questions. And it has always been the case, I think we are talking about interdisciplinary science more so now than before, but I think the interdisciplinarity has always existed. Always existed. We're just talking about it a lot more today because, I don't know, for maybe due to reasons of compulsion, that we have to put our heads together. And that's really what it is.
Yeah. We're also, I think, to some extent, connecting it back to the education system, if you like. For instance, we, for decades of many of us who studied in the 90s in college was about you had a BSc biology or a BSc chemistry. Everything was just siloed, and that it was that department which lived in that building with less interactions. And I've always, when I first came to Korea, I was always fascinated saying, oh my God, we don't have these departments. We have broader divisions, which allows for this kind of mix to happen within a system like Korea. And I guess it might have existed in practice, but did it exist in education? I don't know.
No, it did not. I think we have always, suitcase people into, different areas. And just as what you said, even in my earlier institute, ISER Mohali, a very conscious decision was taken that we are not going to have a physics building or a chemistry building and a biology building. It will be one building where all of these people will be there. And if more people join, a new building will be created. And again, you will have a homogeneity or a heterogeneity over there, so that people see each other, talk to each other, and there is no more mixing of the various disciplines and so on. So I think it's very important for this to happen. And one suggestion I don't like to call it an advice, I'll call it a suggestion to students is that even if you take chemistry or biology or physics or what have you, I think the process of learning is, is very forgiving, in the sense that later on you could switch over to anything else if you wanted to, and there is no big problem. So one doesn't have to worry about the fact that, oh, I've taken chemistry today, so am I going to be a chemist for the rest of my life? No, you can always switch fields. And I can give you my own experience, because it has not been a huge change. When I went to the US, I was very clear. I remember Lakshman saying that he was not sure about what to do at the time he was doing his MSc. I thought I was very sure. I thought I was very sure. I thought I was going to do organic chemistry and then move over to bioorganic chemistry. And that's what I wanted to do. But once I went there, I found the work of a certain professor, one Professor Kelly Houston, who was working on spectroscopy. And that seemed so interesting to me. And I said, forget organic chemistry, I'm going to switch. So overnight, I switched to doing this physical chemistry. So there are a lot of people who have switched fields. I know of a civil engineer who's now doing protein chemistry. So it's perfectly okay. So if you think at this point in time, I want to do chemistry, I enjoy doing chemistry, then just do it. Because later on, if you see that there is something else that is more interesting and I want to switch over, I think the process of learning will let you do it. And it is not going to be, you're not going to be compartmentalized forever. And therefore, at any given point in time, do what you think is most interesting for you at this point in time, without having to worry about what will this take me to later, and what opportunities exist later, and so on and so forth. So I think that should be the way you approach.
Very significant advice, because often students think after 10th, 11th, once they compartmentalize, they don't have the flexibility to move. And what you're saying
enormous
there is very important.
You have enormous flexibility, and people have moved from one end of the spectrum to the other and have done extremely well. And what happens is when you go from one end to a somewhat unrelated subject later on, it's still an advantage, because you carry the tools that you learned in this subject and you apply it to the new area, and others in that area haven't even thought of it, because you are coming with new ideas and new thought processes, and it might actually help in moving from a topic A to a topic B, and topic A and B are seemingly unrelated. It is perfectly fine. And life will let you do it.
Fascinating. Yes. Somdata, if I can come to you a bit about your work with a lot of young people, and where do you see the big complex problems or areas that students can actually work, young science graduates?
That's a very difficult question, in my opinion, because I think every question is just as precious. Like the deeper you go, the more unsolved nature you see of it, and there are ways you work on it. Of course, there are areas that are selling more, and like the big data in biology, for example, all the omics, genomics, metabolomics, and proteomics, those definitely have a lot of financial heavyweight at the moment, but I wouldn't like young students to burden themselves with such things. I really think that it's more important for them to recognize the either one or however many big questions that they think are interesting for them. Find resources on it, talk to experts on it who work on those, and figure out what are those unsolved questions that exist, and then recognize and identify which ones they would like to work on. So one thing, I mean, again, probably I'm coming from a lot of my personal experience space, but when we were younger, we were often asked, like, when you grow up, what will you become? So people would think that, okay, we will become doctors, we will become engineers. And I think that's not such a great way to think of one's life. It's more fruitful, probably, to think of what questions you want to address. And then, I mean, as your life progresses, you figure out you want to address it as a clinician or as an administrator or as anything, as a basic scientist, as a translational scientist. It all falls in its place as you start understanding yourself better, and also the scope around you better at that particular juncture. I don't, I wouldn't advise students to start thinking of what they want to become, but rather what they want to work on in more details, probably.
According to you, what were some of the big problems, complex problems that young graduates will need to kind of focus on, keep the eyes and ears open, where we need more science graduates to actually contribute? So yeah.
Right. I think, and this probably, I'm just going to extend what Dr. Vishwanathan was saying. So I feel, one of the big things we're seeing, and it's a very silent thing, really, there's been a very rapid proliferation of, lifestyle and chronic diseases, diabetes, cancer, cardiovascular problems, and so that's one area that's sort of the research in that area has expanded tremendously. That's something I see happening, more of chronic diseases, because these times are a confluence of all the negative things like bad environment, less activity, too much stress, right? And so I think that's one area that, and so my point is that for that is that there is there is enough hope in healthcare as a research in the capacity of a researcher for that. For instance, also environmental deterioration, right? I mean, this is again like a very pressing issue. We need policy changes, of course, but we also need research into this area. How do you get rid of the refuse and the garbage that human settlements generate? Right? It's a very pressing problem, and like you can address this as a biochemist, or as even like a policy maker. For instance, energy production. I think that's a really big area that needs to be addressed. Now, what are we going to do in the future about energy production, a sustainable way of, and this will require people of all disciplines, right? How can you make use of alternative forms of energy, so I think these are big areas that I think are need, where students can. I mean, these are not exclusive of other areas. You can find your niche, but these are I think the big areas that will be very prominently, visible, very visible. I just want to extend what Dr. Somdata she was saying. She's talking about interdisciplinary stuff. Like a lot of, for instance, a lot of basic science has resulted in a lot of data being generated, and now we have the technological capability to look at to look at, say, for instance, a biological system as a system. We call this systems biology. You have the ability to observe these things at the systems level, and that's. But you still need a grounding in basic science. You can also look at a problem directly from a systems biology perspective. But that's another area that I just wanted to add to what Somdita was saying. I'm not sure if I'm missing something, but I should mention that the skills you acquire as a PhD in your doctoral studies are completely transferable. And just to extend what Vishy was saying, so they're completely transferable. I mean, you can take, you learn how to write, you learn how to think, you learn how to speak, you learn how to ask questions, right? Because inquiry begins from a question. And you can take this set of skills and you can apply it to other areas of biological science, maybe with chemistry or physics. Yeah, so,
Fabulous.
I think I'll stop.
Yeah, no, I think the area of what you touched on, energy, is pretty critical. And just to your last point as well, I just wanted to also remind our audience that we have this at Kriya. I know that students all go through a scientific reasoning program in the first year. So irrespective of what they come to study, the thing about the mathematical reasoning and the scientific reasoning is actually put in there, which is about more a skill of process of addressing and comprehending a problem and addressing it. Professor Shiva, if you've joined us.
Yeah.
Thank you.
So you are asking about some of the major questions that probably physics candidates will have opportunity to work on. It can be in very basics of physics, like asking questions of, do we have a final theory of physics? So what we currently have is what is known as a standard model as far as extremely small objects are concerned, like particles and subatomic particles. And we have a corresponding standard model for the cosmology as well. So we don't understand much of it. So what we have learned about this entire universe is by looking at what is known as matter, which is about 5%. The remaining 95% is in the form of either dark energy or dark matter, about which we practically know nothing. Okay. So there are a lot of questions for people to really look into, because people think that it is waiting for youngsters to jump in and solve. So that's one. Now at fundamental level in other subjects, like for instance condensed matter. So there has always been a dream as to if we can get to superconductors which will be superconducting at room temperature, almost all our energy problems are solved, and that's a dream. And whether we can make such a material, or are there in principle impossible results? Suppose if somebody comes and tells, no, it is impossible, so long as these are the physics laws, it is impossible. That's a fantastic result, but we don't know, totally uncertain, which Kriya emphasizes so often. So we have not found the answer to that question. Okay. The important other domains where physics graduates can find very interesting problems is one of complexity, which applies across disciplines, be it biology, be it the formation of the universe itself. Complexity theory seems to be holding key for most of these things. And once again, energy and environment, in both the cases, physics will play a major role. And so those of you who are interested in pollution, environment, may have heard about something known as a Dyson sphere, which he said we can put some kind of reflectors all around the sun and focus energy onto the earth, so that we can get rid of all the energy requirements from fossil fuel and generate as much energy as you want. So long as the sun is there, you have an energy source. These are all very crazy ideas, but who knows? Crazy ideas can become the reality one day. Maybe, and of course, there are many other interesting technology-based issues like industries face and other disciplines face where physics can contribute. I will just close with one anecdote from IBM. So when IBM made personal computers, the chairman of IBM, when he was asked how many computers they are planning to make, he said, possibly there is a market for 4 computers in the world. Okay. Right, I was telling K.S. Vishwanathan the other day, probably there are only 4 homes in the world now which do not have a computer. Okay, so it is extremely difficult to predict what will become reality and what will become something that we can't do away with. So keep that mind, open mind, learn your subject well. You will find opportunities to excel in any area later. That much I can tell you.
Thank you, Professor Shiva. And I'm sure that working with now 2 batches of students, you're always hearing some sorts of crazy ideas. So do you want to just, I'm going to put you on a little bit on the spot here, but asking you yourself lead to 1 or 2 interesting research projects. Do you just want to kind of maybe hint a bit about What is it that you're doing, and where are students actually working on currently with you at 3R?
Okay, so I have two. One, we are with my colleagues from chemistry. We are trying to actually see whether we can do what is known as a small desktop like quantum computer. Okay, so it is on paper now, but with the sufficient support, we are hoping to say that we'll be able to make one with, of course, collaboration from few other institutes, maybe ISER, Mohali, and IIT Chennai, where probably every school can have a demonstration equipment of what is known as a quantum computer. This is one that I'm working on. The another one that I'm trying to, where some of the current undergraduate students are doing project, they'll be doing it in the summer, is to understand a system which has got many particles in it. So we are made up of millions and billions of molecules. Okay, when I look at each molecule, there is nothing like you cannot expect there will be something called life, there will be something called consciousness. But when these molecules are put together, we are more than a bag of molecules. Okay, we seem to get some additional properties which we call as emergent properties. So two of my students who will be doing a project with me where we start putting particles one after the other with a certain interaction switched on, and we want to see at what level it will generate properties which you would not have expected just from the behavior of individual properties. So this is what I am currently working on, and yeah, maybe I'll.
Thank you. Thank you so much. We'll move definitely to some questions, and I'll pass that to you. And I know Rita Subramanian, you posed a question on can we add a dimension of mathematics? We didn't particularly in this panel because we have a dedicated panel for mathematics coming for you on the 15th. So we just thought we will keep this quite aligned to the core sciences for sure. And so with that, I'm going to now ask some of the questions that had come in earlier. And I'm not too sure whether this is, I'm going to keep it open. I'm not too sure who exactly will actually talk about it, but this is more on marine biology. Any kind of insights? I'll leave it to the two biologists to kind of insights. So this is about a question on, what's really marine biology and what's really happening in that space, and one could build upon.
I'll take that question because CSIR at the moment is looking into it quite aggressively. So India has a huge marine coast, and much of it, the marine life remains undocumented and unstudied. So actually, as we speak now, there's an expedition running where there's a ship that's collecting microbes and other organisms from the marine coasts of India, and they aim to look at the proteomics and genomics of it and see. I mean, basically, they're going to characterize and possibly come up with some answers on what makes them unique. But it's hugely undocumented, uncharted, and biologists definitely feel that there's a lot of potential to look into it, and it's almost exploratory. So it's not like they have a clear agenda of what they want to find out from it, but rather it's an adventure expedition, and you find whatever you find.
Sure, thank you.
I thought maybe I could ask her a question. I don't know.
Yeah, please.
So does the CSIR have any plans to put in place like an institute for marine biology? I mean, is there any plans in that direction?
I don't think there's any talk of it right now, but there's definitely an oceanography institute which is already in place. So okay. The NIO, as it is called, so that's the one which is undertaking this expedition at the moment.
Thank you. So I'll leave that next one to Professor Lakshman. I have one more biology and then we'll move ahead. So this question comes from Pranav Jain. Pranav, thanks for posting this. So he says, the world of today sees a growing need for research and knowledge based on the biological aspects of human health. And the solution to a great extent is in natural extracts. So if we want to make a career in this space to give better answers to the world, what is the right path to take?
Okay. That's a nice question. Some of the there has been some resurgence of interest in looking at the remedies that have worked for centuries. I mean, can we revisit these remedies, these home remedies, and through a more modern scientific approach, empirical approach, to see what it is about a particular remedy that makes them effective. they are effective. We know they're effective from experience. And so, and these remedies are normally made of some extracts, and there is, I know for a fact that there is an institute in Bangalore. I forget the name. I think it's called Vyasa something, but I think part of its mandate is to apply empirical biological methods to studying yoga and to studying Ayurveda. So there has been some interest in this, and it would be nice because the pharma companies are sort of, there aren't enough drugs coming out of their pipeline, and it would make sense to look at something that we know from experience, observational experience, that it works. And so I think it's important not to, it's important, there's nothing about belief here, right? I mean, we are scientists. Yeah, we try to explore something for ourselves and determine if it's correct. So I think we need to, there has to be change in mindset also, and we need to we need to invest more time and money and effort into researching what the conventional remedies and such, Ayurveda and yoga, they all merit some degree of scientific exploration. So I'm not sure how far ahead we are in this. I'm not sure of government policies in this regard, but that is something, for instance, curcumin, right? I mean, turmeric. That's actually like an area of like intense research. So there is also what we call, we call it, the concept of using uh, food, nutrition as therapy is still alien to Western, biomedical science, right? I remember the doctor, a cancer patient receiving white bread for breakfast, and white bread and jam. Now that is an absolute no-no. I mean, tumors love sugar, right? And so, I mean, the ideal food would have been like fruit juice, right? And so I agree with the question that, there has to be some investment, and maybe we can lead the way because we already have a corpus of knowledge in this regard, in our Ayurvedic scriptures.
Yeah.
I think,
Absolutely. And the whole, what's been fascinating, you mentioned turmeric, but as I remember last year, there was this whole economics of turmeric and what was happening around the world in terms of where one part of the world was dumping turmeric and the other was actually desperate for it. That's interesting.
Look, can I just add on something? Can I
Please,
just add on
yes,
something to what Lakshmi
absolutely.
said? I think it's a good area of research or a good question to ask, as to what the extracts from natural resources have to do as a for medicinal values. And even if you go back in history, the cure for malaria, which is quinine, which was actually got from the bark of a cinchona tree. It's found quite by accident. I mean, they recognized that this is what it was. But then what happens after the isolation of the active ingredient is, once you know it is quinine that's doing it, but then to use it as a medicine, you can't rely on natural resources for your world demand. So at some point, you have to start making these molecules in the laboratory and then in the factory just to meet the demands. So the isolation of the compound and recognizing what is important, it doesn't stop there. It then moves on to the next phase where you have to make the molecule synthetically just to meet the world demand. So you can see that there is a lot of biology and chemistry that comes together to extend that question.
Absolutely. No, fair enough. Professor Shiva, I'm going to ask you this question, and that's just putting you in the spot of as div chair at Kriya. And this is about the connection of biology with psychology, in terms of where do the both go together. So there has been a question there. So I'm just, is that something that you want to kind of talk about?
Sure. Yeah. Maybe Lakshman and others can also chip in and assemble it. Okay. So first of all, we all know that our what we think causes changes the way we in the parameters of our system. BP goes up when we are angry. Dot dot dot. Okay. And obviously, there is a need to understand that what's really causing these kind of changes in the system. Okay, it seems to be a thought. Anger is a thought, but the effects are totally physical. Okay, and if you want to really understand this, we need to understand both biology and psychology. And that is something that we, for instance, I heard people saying that brain is after all a bunch of neurons, and that's it, you are a bunch of neurons. And but there are also school which says no, we are beyond that. Okay, so I have listened to Professor P. Balram, who, in fact, the word that I said, I am more than a bottle of molecules, is essentially a quote from Professor Balram. So he did not believe that if I put all the molecules together and shake a bottle, you can produce a human being. That's not going to be so. Something more is there. Maybe when we come to some stage where we understand this. So biology and psychology, of course, they are very related field, though they were studied as independent fields long back. But now you see, like, even psychologists are trying to read MRI. They are trained to read encephalography records. So, okay, so it automatically tells you that psychology is not just asking questions and trying to get some information about the person you are talking to. It is also trying to relate it to what's really going on at a physical level. So, okay, this is it. And this is also one place where I have a feeling that going by what I see in literature, that mathematics plays a role. Somebody asked a question, okay, and not to connect what's really happening at a psychological level and what's really happening at a biological level, we need models which will actually try to connect the two. These are called as cellular automata models. By simple rules, you will be able to produce this kind of experience that we get. Okay, so this is where it is. Maybe more details can come from specialists here, but this is the sense that I get by talking to my colleagues both in biology and psychology in Korea.
Anybody wants to add? Yes, Professor.
Maybe, may I, Kala?
Yes, absolutely.
I think just to add to like what Shiva was saying, so I think one area of biology specifically that is very complements psychology very well is neurobiology. So, and again, you can come into neurobiology through the regular biological science pathway. So that's really something that I was speaking to one of my colleagues here, and she would show up in one of the panels later on, Miss Anusnigdha, and she did say that as a psychology student, they always had a neurobiology course. I think so certainly that is important. There are other ways, but I think biomedical techniques to observe a person. For instance, we use wearables these days to keep track of our bodily functions, body activities, sleep information, right? And so all these can be used to add up and help the psychologist in assessing the patient better. So I think I'll stop.
Yeah.
Maybe I just want to add just one sentence.
Sure.
This has a history. So philosophers used to call it a mind-body problem. Okay. So it is some clarity is emerging now, basically because of the advanced technology we have, instruments we have. But this has been questioned for a long time, like what it means to say that I have a mind. I have a body which I know is matter. What is it? What does it mean to say that I have got a mind? So it's called a mind-matter problem in philosophy. So now, if you think now, all the three get connected. So biologists and psychologists may actually come up with an answer. May not be the perfect answer, at least some guidance we may get.
Yeah. Thank you. I'm going to ask Professor Vishwanath in this, and I know he hinted upon this in one of his responses. So this seems a very genuine concern from one of the audience members, and says that natural sciences seems hard. I'm currently a 12th grader, and I find that my deep interest that I had in sciences is not there anymore. So I like the science, but I'm confused whether that's it. So any words of advice?
Kala, I lost you for both parts in between. So I only sampled you a little. So
okay, no worries. So one of the concerns is that switching from human sciences to natural sciences seems hard. And I'm currently doing my 12th standard. I feel that the deep interest I had started in sciences is not there anymore, and I'm confused now. So maybe what's the best way to find direction? Maybe that's...
best direction is to join an institute in which they will start you off with different areas, like in Korea, for example. You get a grounding in social sciences, you get a grounding in arts, you get a grounding in science, and so on. And after listening to the different people teaching you different things, then maybe you can have a rethink on what you want to do. Then find that, yes, science is really not that boring. It is a lot more interesting, then maybe you can come back to science. Or if some other person in literature or economics or whatever has interested you so much, and that is what you want to do. And as I said, I mean, the learning process is very, very forgiving, and you can always move from one to the other, and therefore it's very, very possible. But Kala, before I go any further, I just want to add on to what the discussion was going on psychology and this thing. I had, and this is a question which I had in my mind, and I would ask this question every time I listen to a neurobiologist giving a talk. Because as a chemist, I believe that everything that happens in your mind has to be at the molecular level. So if I'm talking to you now, it is because some molecules have changed position, that have done some changes in the structure, produced an electrical impulse, and that is what comes out as speech. And same thing with memory. I've seen you today. I remember you to, recognize you tomorrow. It's because I've recalled that memory, and even that I believe has to be, at the molecular level, explained at the molecular level. So every time I ask these people who give talks on neurobiology, are we anywhere close to understanding this at the molecular level? And the answer is no. We are very, very, very far away. But they all agree on the fact, yes, that it has to be at the molecular level. So it is not just biology and psychology, of course, is more human behavior. You look at it in a more, not at the molecular level, you just look at the response level. So you have psychology, biology, and I think you also have molecular biology, which should then put all these together for a very deep understanding of what psychology really is. So I think eventually it has to come down to understanding these at the molecular level. Yeah. To go back to the student who asked this question, I think if you're still interested in science, I think it might be still worthwhile to take one more shot, by taking a course in some sciences in the first year, for example, and then deciding for yourself if that is what you really want to do. In ISER Mohali, we had the same philosophy. Everybody who joins had to take had to take courses in math, physics, chemistry, biology, and humanities in the first 2 years. And then at the end of the second year, they would decide whether they want to go into math, physics, chemistry, or biology. So which means essentially they get a chance to rethink as to what it is that they really want to do. And Kriya, I think you have a wider option because you are not restricted to just sciences. You can decide from anywhere, being in social sciences or economics or what have you, to being in sciences like physics, chemistry, maths. So yeah, so if you still like chemistry and if you want to sciences and you want to have a go at it, maybe courses in the first year will help you do that.
Yeah.
Kala, can I add a few things to what Professor Vish said? Okay.
Sure.
So one good thing about 2000, beyond 2000 is there are fantastic accessible articles which are fairly accurate. Just because they are popular articles, they are not inaccurate. They are available currently, which was not the case before 2000. Okay, it used to be textbooks, which would practically will be so daunting to read through the textbook, gather what the subject is all about. But that's not the case now. You have articles written fairly well written by top-notch people and very accurate at all levels. I can, for instance, convey ideas of even cosmology or particle physics to a 12th standard student. Those kind of articles are available now. So it's just a question of searching for the article, read, and who knows, you may get interested even during this summer. You don't have to wait for really join and explore.
Yeah, I know. Absolutely. I know we're going to come to another close, a couple of more questions, and we close this, and all the questions on admissions will be handled after this panel discussion. We're primarily taking a lot of science related questions, but after this, you have a team available who will answer all the questions regarding admissions. I know there's just this deep dive into biology that's happening here. So there's another question that actually comes in saying that if I'm a student who has not done biology, what is the hope of me taking up, let's say, biotechnology as a career, either at an undergraduate or otherwise, and this whole space of how biology and biotechnology actually differ? Professor Lakshman.
So I'll just, maybe Lakshman will add. I will tell you, as far as Kriya is concerned, we don't demand that you must have done biology in your +1, +2. So it's without doing bio in your +1, +2, you can still take our BSc honors in biosciences. And from there, of course, you can branch off into biotechnology for your masters. We also believe that at an undergraduate level, specialization is no good. Okay, you should get a broad exposure, and then whatever you specialize, you will see that you are really well grounded in the basics, that you have absolutely no problem in contributing to what you specialize in. So if it is Kriya, you don't have to worry about your +1, +2 specialty. You could have done economics, history, accounting, and still you can emerge or blossom as a top-notch biotechnologist.
Thank
Of
you. And
course,
I'm going to get Professor Lakshman to respond to that, as well as add on, Professor Lakshman, into this bit about specializing in your bachelor's, this whole idea of, I want to do bachelor's of genetics, and I want to, students kind of coming with that absolute end, and we've time and again said, get your foundation in place. So yeah, your comments on both those questions.
Okay, so I'll just go back to the other question first.
Yes.
For instance, my master's, my advisor at JNU, Dr. Sneha Sudha Komat, he started off at the Indian Institute of Science studying statistical mechanics, which was an offshoot of quantum mechanics, right? And then she quit about 3 years into her course, and she did her PhD in the biological sciences. And then she was my mentor there. And she could give the most exquisitely beautiful explanations of biological phenomena. It was just beautiful. I mean, she would interpret fluorescent spectra so beautifully. So my point is that, actually it's, and so I can give you another example, right? I've sort of migrated into this area of say personalized health, which is an interest certainly. And this company that I was working with, so now you have, for instance, you have collected all the data about about an individual's health, and now how do you use that information about the person to predict the person's health in the future, right? That is done by a Bayesian mathematical model. And so, I find that my friends and my colleagues in the biological sciences who are doing very well are actually those who have started off doing either physics or chemistry or mathematics. It's just beautiful. I mean, because they bring this lovely perspective. They don't have biology in their blood, and they can like give a really nice perspective, to their studies, to their work. So essentially you don't need to have biology as your undergraduate major to come into biology later on, right? So the other question is, in the biological sciences, really, at the undergraduate level, please feel free to do whatever you're interested in, right? I mean, they all converge at some point, right? I mean, the fact that you do genetics or microbiology or biochemistry at the undergraduate level, you'll do some of everything at this undergraduate level anyway. You don't need to specialize at this level. You cannot. It was a very humbling moment in my PhD when my PhD advisor, we were having a cup of coffee, and then he said, I had just graduated, and I thought I was king, right? And my boss said, Lakshman, the PhD is the entry level degree into the biological sciences. It was very humbling, right? I mean, so you please feel free to do. I mean, to all those who want to super specialize at the undergraduate level, please don't go in that mindset, right? Get your basics right, understand the subject, and try to specialize and specialize. The specialization is at a premium these days. Your brand value comes from the deep expertise, the deep knowledge you have of what works, what doesn't work in biology.
Thank you. Somdata, do you want to add any comments to that discussion? This whole specialization bit that we're talking about.
Sure. Especially, I mean, because the discussion started with biology and I am trained in biology myself. I have had friends and colleagues who have joined biology during their masters with a background in physics or chemistry. I have had colleagues or seniors rather who have done all their training even until PhD in physics or chemistry, and then have opened a lab in biology and have excelled. And then of course there are people like me who have been trained in biology all throughout their career. So biology, I mean, I think the entire discussion today somehow has been hugely centered around biology, and also because the most exciting unsolved questions are around understanding life, and probably much of the discussions today have been because of that, around biology. And you'll see, if the most exciting discussions are around life, then you will want all kinds of expertises and philosophies to come together. So it really does not matter when you want to get into biology head on, but I completely agree with what Lakshman says, that bring in your own specialization so that you know exactly that, okay, you're looking at this question in life, but you're looking from this lens, and that is going to be your USP. So I think that's what is more important rather than thinking that I have not been trained in biology. On the contrary, ever since I have moved to Telangana, I mean, most of my training happened in Bombay and then in Germany, and then I moved to Hyderabad. And I was then introduced for the first time to a system where literally people who are studying biology are not studying mathematics after their some of them right after their class 10. I think that's hugely detrimental, because biology the way it is today just cannot function that way. And I think that's an extremely myopic view, probably something that they thought works well for training for medical sciences. I even doubt if that is useful there. And definitely it's not useful if you're going to pursue academic biology.
Yeah. No, I think it's a very important point, and we didn't have Ms. Meeta Sharma because really we wanted to have that school. But that's really where it begins to happen, right? After we learn everything up to grade 10, and then they start to silo you a bit about that's it. Now you take a science group and you can't really touch anything else, and you're just siloed at school level, and then suddenly you're now saying, okay, you can actually do everything. So I guess it's a huge mindset shift that needs to happen. I want to give the last couple.
If I
Yes,
may
Sumrata.
also add on to the psychology bit. I mean,
Yes. Yes.
I know that all the other three panelists have added a lot of useful views on that. So my master's and PhD training has been in neuroscience, and if I may compare, what I found extremely useful when I was in Göttingen is the hugeness of the departments who look into neuroscience in different ways. So there's neuroscience and there's neurobiology. Then there's medical sciences which come into place. And I think to work on a question like this, you really need to be in a space where all these kinds of disciplines can crosstalk with each other. Then you can identify, okay, my specialization is either into molecular biology, so molecular neuroscience makes more sense, or cell biology, and hence cellular neurobiology makes more sense, or medical sciences and hence psychiatry or psychology makes more sense. But actually, for how nascent the field of neuroscience is, there is no replacement for being in a place where you have access to all these disciplines and expertise talking to each other.
Very well put. Very well put. Thank you so much. We have a minute, and I'm going to ask Professor Shiva to just close this with one observation for the audience, which will leave into the Q&A with Outreach. What are we doing different in terms of teaching sciences at CREA, Professor Shiva? How are we approaching it differently?
Okay, actually, sciences in CREA has maths, physics, chemistry, biology, computer science, and psychology. So all these things are under the umbrella of the sciences. Okay, so what is the difference between what you would do in a regular but a good college and CREA? In CREA, actually, we have reorganized the entire syllabus so that you see the coherence of the subject. Okay, even in a subject like chemistry, for instance, if you take, I remember people will say physical chemistry has practically nothing to do with inorganic and has nothing to do with organic, but that is all shaken in CREA. Okay, so Professor Vishwanathan will teach the first course. He will talk about molecules. He will draw examples from all organic chemistry, inorganic chemistry, and physical chemistry to explain concepts. So first, those barriers are broken, and second thing, we rely rather stress upon what we call as immersive experience. So what you learn in your classrooms, you have to go to the lab and practice. So in our lab, we don't have a record notebook where we exactly write down as given in the manual, fill the table and paste it. No, we don't have a record notebook in the first place. So you will come with a bunch of papers. You will be told this is what you have to do, and the instruments are there on the table. You have to go figure out what to do the experiment, then compile your papers and give it for assessment. That's one. The third part of this immersive experience, at least in physics, what we are doing is each batch of students will make one instrument by using all that they have learned, and this instrument should be of such a quality that the next batch will use it as part of their lab experience. So we have got things like a 3D printer and a small workshop. So students will be sort of asked to design this. Of course, we will provide some basic idea what is the kind of instrument they can build, but they are going to build it. So that way there is a practical aspect, there is learning in the class, theoretical aspects, and then this will actually help them to integrate the two. So that will be, in our opinion, a complete experience.
Thank you. There couldn't have been a more exciting time to be a science student if you are. And I want to go back to our title saying it is infinite possibilities. You've heard all our panelists. I mean, there is no just singular path that science actually takes. We're seeing increasingly how it's traversing across, whether that's agriculture to environment to the big data to the physical world, across the entire spectrum. So thank you so much, panelists, for your very detailed but very relevant and relatable responses. We couldn't have asked for a more diverse perspective, but all probably singing from the same page as well in that sense. So thank you so much, and thank you for being here this morning. Bhakti?
Thank you so much, panelists. Thank you. Stay safe, and we will see you soon for another dialogue. Thank you very much.
Thank you.
Thanks,
Kala.
I quite enjoyed it, and thank you very much.
It was really enjoyable. A lot of learning as well.
Thank you.
Thank you so much.